All right, let's dive in. Today, we're going to talk about something that's, well, it's both beautiful and sometimes super confusing: recursion. It is an incredibly powerful tool, and by the end of this, you're going to have two solid patterns to help you master it.
I mean, it really comes down to this one question, right? How on earth can a function solve a problem by just calling itself? It sounds like it should just run forever.
And yeah, if you're thinking, that sounds like a paradox, you're not wrong. It feels like one. But trust me, once this clicks, it opens up a whole new level of problem solving. It's a real game changer. So to get our hands dirty and make this real, we're going to stick with one simple challenge the whole way through: summing up the first n numbers. You know, if n is 3, we want to get 1 plus 2 plus 3, which is 6. Simple. Okay, so that's the mission. We need a function that, whatever number n we give it, can figure out the sum of all the whole numbers from 1 all the way up to n. Look, you could totally solve this with a simple for loop like you see on the left. That's the iterative way, and it works great. But today, we're not just hunting for an answer. We are trying to understand a deeper pattern. So we're going to focus on the recursive way. And that brings us to our very first pattern. I like to call this one the carrier. The whole idea here is about passing the answer down the line. Okay, so the fancy term for this is parameterized recursion. But forget that for a second. Just picture this. Someone is walking down a flight of stairs and they're carrying a basket. On every single step they take, they add something new to that basket. The function literally carries its progress with it. Okay, let's trace this for n equals 3. Watch this. We start by calling our function with our number, 3, and an empty basket, a sum of 0. That function does a little math and calls itself with the next number down, 2. But look, it passes along the new sum, which is now 3. The next call takes that 3, adds 2, making the sum 5, and calls again with 1. And finally, it adds that 1, bringing the basket's total to 6, before making one last call with 0. And boom! The second our function gets called with the number 0, it stops. It hits what we call the base case. The trip down the stairs is over. So what's in the basket? The number 6. That's our answer. The function just prints it out, and we're done. All right, pattern 1 is in the bag. Now let's look at a totally different way to think about this. I call this pattern the builder.
So the formal term here is functional recursion. Now, instead of carrying the answer down, each function does just one small piece of the job, and then it waits. It basically turns to the next function call and asks, hey, can you figure out the rest of the problem for me? I'll wait. The final answer gets built on the way back up. So check this out. When we first call sum of 3, it kind of stalls. It can't give us the final answer right away. It knows the answer has to involve the number 3, but it has no idea what the sum of everything below it is. So it just pauses and asks, okay, what is 3 plus whatever sum of 2 comes back with? And this is where things get really wild. You get this chain of waiting functions. The sum3 call is just sitting there, paused, waiting for sum2. But sum2 is also paused, waiting for sum1 to finish. And sum1 is waiting for sum0. They're all just frozen in memory, waiting for the very last call to resolve. And here's the beautiful part: the return journey. Finally, sum0 hits that base case and just returns a simple 0. That 0 gets passed back up to sum of 1, which can now finally finish its job. It says, great, 1 plus 0 is 1, and returns that. Now sum2 gets the one it was waiting for, calculates 2 plus 1 is 3, and returns that. And at long last, our original sum3 call gets its answer and calculates 3 plus 3. And there you have it. We get the exact same answer, 6. But the logic was completely flipped, right? The result wasn't carried down in a basket. It was built, piece by piece, on the journey back up. Okay, so the best way to really know if you've got a pattern down is to apply it to something new. Let's put our builder model to the test with a classic: factorials. A factorial is almost the same as our sum problem. Factorial of 3 isn't 1 plus 2 plus 3, it's 1 times 2 times 3, which also happens to be 6. So can we just take our builder code and swap the plus sign for a multiplication sign? Seems easy enough. Let's try it. Here's the code using that same pattern. We changed addition to multiplication. Everything else looks identical, even our base case. When n is 0, we just return 0. Seems logical, right? But oh boy, watch what happens. Factorial 3 waits for factorial 2. Factorial 2 waits for factorial 1, and factorial 1 waits for factorial 0. The base case is hit, and factorial 0 returns 0.
that 0 gets passed up, so what's 1 times 0? It's 0. And 2 times 0? Also 0. And finally, 3 times 0 is 0. Our answer is just wrong.
And here is the huge aha moment. The base case is everything. For addition, the do-nothing number, the identity value, is 0. Adding 0 doesn't change anything. But for multiplication, the identity value is 1. Anything you multiply by 0 becomes 0, which completely breaks our chain. The simple fix of changing the base case to return 1 solves the entire problem.
Before we finish up, we have to talk about the cost. Recursion is elegant, for sure, but it's not exactly free. There are some performance things you got to keep in mind.
For both patterns we saw, the time it takes is proportional to the number n, what we call O of n. That makes sense. For a number like 3, we made 3 main calls. But what's really crucial is that the memory space it uses is also O of n. Remember in our builder pattern how sum3 had to wait? Each of those waiting functions takes up a little slot in memory on what's called the call stack. So for a huge number n, you could have n functions all stacked up, just waiting. And that brings us to the end. We've looked at 2 totally different ways to think about recursion. The carrier passes the answer down, and the builder constructs it on the way back up. They both work, but they are fundamentally different mental models. So the question I'll leave you with is, which one just clicks better in your brain?